Hey guys, today we're going to be working on topic 6.4, which is another branch in which we go through nomenclature or naming called stock system. And so we're going to work with all of those transition metals that we've kind of been ignoring. So a few things before we get started. If you want to pause this video at any time to add this, please do so. So if you want to recall, transition metals are what I've outlined here in orange with the inclusion of tin and lead. So metals in the alkaline metals, alkaline earth metals, aluminum have predictable number of electrons. Remember, these groups that sit above are the representative groups. And so these guys have predictable valence electrons that they're going to want to lose. And then as we go to the nonmetals in the halogens, oxygen, nitrogen, and carbon families, they have a predictable number of electrons they want to gain. The issue is those elements in groups 3 through 12, or the D block of the periodic table, do not have a set number of valence electrons. And so because of that, they can form ions of a different charge. And so because of that, we have a different branch in which we work with these. If you remember, these groups with the oxygen, nitrogen, carbon, and boron family, these are blended families where they contain a mixture of nonmetals, metalloids, and metals. And so tin and lead are going to follow the same pattern. Some of these other elements down here do the same, but we don't really work with them. Tin and lead are the two that we're going to use a lot. So tin, lead, and then that D region there. So that's what we're going to work with today. The other thing is you will need your polyatomic list. And so one thing I made a note, but in case you didn't see it, acetate is a polyatomic that can be shown two different ways. So just one thing you may want to take and make a note and add this to it is one other way that acetate can be wrote is CH3COO with a -1 charge. So these have the same chemical composition. It just depends. Organic chemists tend to use this top one here. And then basically if you're not an organic chemist, they tend to use the bottom one. So it just depends. So please add those two things. So let's kind of dive right in. I will tell you my hands are having a particularly rough time today with writing, so hopefully it's not too terrible and that you're able to read everything okay. So like I've already said before, transitional metals can form multiple ions. So we have a way that we account for that because you get different compounds which have different properties. So we do need to indicate what the charge is to understand what it is we're working with. So again, as we build on naming, there's going to be things that carry on with us and things that we add on to it. So when we name transition metals, we have to include a Roman numeral to indicate the charge. So when we go to name a metal, we name the metal, and then in parentheses, a Roman numeral with charge. So before I go any further, and in Google Docs, I have a love-hate relationship with it. I wanted to add a little table with Roman numerals as a refresher, but it was not letting me place it nicely. So just somewhere on the note page or somewhere that if you want to add it to like the back of your polyatomic list or on your periodic table, whatever floats your boat works for me. But just to recap, in case you don't know your Roman numerals, for the number 1, we show it as an I. 2 is 2 I's, 3 I's, 4 we show it as IV, 5 is a V, 6 is VI, 7 is VII, and 8 is VIII. And for the most part, that takes care of our charges. There isn't many transition metals that really go past 5. A lot of them are in the 1, 2, 3, or 4 range. So just a refresher on that. So here you can see that we have the element Fe. If you look at your periodic table, these are both iron. But notice here, they have 2 distinct charges. So again, these are 2 different forms of iron. They are going to give us different properties. So this we would call iron. In parentheses, we will have, because it's a +2, we're going to put a Roman numeral 2. Here, because iron is a +3, we would call this iron 3 with a Roman numeral 3 following the parenthesis. So again, two distinct forms of that cation. So part of this naming system is relatively easy. The other part's a little bit tricky. We're going to start with the easier half right now, and that's with coming up with the formula. So a lot of this is no different than we did with 6.1 with binary or 6.3 with polyatomics. So one thing that is really nice is you can see here in this first example, we have copper 2 chloride. So copper 2, that tells me the charge of it. So you're not going to go to your periodic table to find the charge of copper. The name has to tell you it because, like I said, there's different varieties of that particular cation. So we write that as Cu plus 2. Now the part you have to be careful of is I have a blend of polyatomics and non-polyatomics. So we do have polyatomics like chlorate and chlorite. This has a suffix of "ide." That tells me that that was chlorine that changed to chloride. So I know that chloride is Cl. If you need to use your periodic table, it's a -1 charge. Now at this point, everything is no different than what we've done. You cross down, and this becomes Cu, Cl2. So like I said, this is in a way almost easier because the charge is given directly to you. So here we have lead 3. So you may have to look up the symbol for lead, but lead is Pb, and that is plus 3 because that Roman numeral there. Nitride, again, won't be on your polyatomic list. A good indicator for that is that "ide" suffix. So nitride is nitrogen off the periodic table. Again, looking at charges, it will be a -3. You may notice this right off of the bat that the charges cancel. So these simplify down essentially to 1 and 1. So no subscripts really need to come down. And this just becomes P, B, N. And that's your final answer for that one. So lead 4, so the symbol for lead is still Pb, but the difference from the one up above is we now have a +4. So this kind of explains an old naming system. So lead and Pb have nothing in common. So in chemistry, depending on the charge that you were working with of your cation, lead used to be that you would use Plumbic or Plumbus. Copper, for example, copper is Cu. There's copper with a +2 charge, and then like copper with a +1, and they'd use cuprous and cupric. And so iron was ferrous and ferric, which is why the symbol's Fe. So if you've ever wondered why do some of the symbols and names not match up, that's why. It's based on an older naming system that isn't really used as traditionally anymore. So oxide, ide ending, so that tells me we're working with oxygen -2. Same idea, we're going to cross down. So Pb is going to get a subscript 2. Oxygen is going to get a subscript 4. And again, you want to make sure that you're looking for, can you simplify what you can? Both subscripts are divisible by 2. So your final answer is PbO2. So again, you will see more instances with simplification with stock system than we saw previously. So over here we have mercury 2 hydroxide. So we still have our Roman numeral. So mercury's symbol is Hg, +2 because of that Roman numeral. So hydroxide. So yes, I know that it ends in ide, but if you look, there's no element that came from. This is one of the couple of polyatomics that do end in ide. So again, if you look here, hydroxide will be right here under the -1 column. And so then it's OH, and it has a -1 charge. So now we're just blending this new stock system with the rules of polyatomics. So we're at the point that we're crossing down. Hg will not get a subscript. It's just going to have a 1. OH is getting a new subscript, and OH is a polyatomic, so you must use parentheses. And the new subscript goes outside, and that's your final answer. Here we have zinc 2 carbonate, so zinc is Zn, and we have a Roman numeral 2, so +2. Again, look at your ending, 8, that tells you polyatomic for sure. So again, you can look through your charges here. Carbonate is here under the -2 anions. It's a CO3 -2 charge. You can see what's taking place here is that the charges are going to ultimately cancel. That means no subscripts are, extra subscripts, I should say, are being brought down. So no parentheses required in this example. So it just becomes Zn, CO3, and we are all done. Last example is titanium 4 sulfate. So titanium is Ti plus 4. Sulfate, again, if you utilize your polyatomic list, it's actually kind of here off my screen. So SO4 -2 charge. So now we're at the cross down step. Titanium is going to get a subscript, so Ti2. SO4 is going to get a subscript, so that means the SO4 goes in the parentheses. The new subscript goes outside. And then you are not quite done. We can simplify like we did here on the example on the left. However, you can only simplify subscripts due to charge. So I can simplify this 2 and this 4, nothing else. So those are both divisible by 2. So my final answer is going to be Ti. SO4 will still need parentheses, and that 2 will now be outside of it. And that's your final answer there. So like I said, I felt like this part is pretty easy, just using kind of skills that we've been using all along so far in this unit. Now, this is where things get difficult. And the reason why it gets difficult is students do not follow these steps. If you follow these steps each and every time, then things will come out correct for you. The issue that becomes challenging is the formula you see might be lying to you with figuring out what is that Roman numeral. So what we have to do here is figure out what is the Roman numeral going to be for that cation. Like you saw up above, there are instances where charges cross down. There are no subscripts. There's charges where they simplify. And so we have to look at what took place. So here, the first one we have is CuCl2. So the first thing that you do in these is the idea is we have to figure out what is that charge. So what you have to do is you cross your subscripts back up, because what we need to do is determine what is the charge of the cation. So what I'm bringing up here is a +2 to the copper, and I'm bringing up a -1. What we're looking for is, did charges cancel or simplify? So the next step is you always, always, always check your negative. Because chlorine is off the periodic table, we just have to verify that chlorine is a -1, which that is true. So that means that this charge here is correct. Now we're ready to name it. So like before, we have copper, that's Cu. The difference is we now need to include that Roman numeral in a set of parentheses following that with its charge, the charge of the cation, so the positive. So this is copper 2, and then this is just chlorine, so it's not a polyatomic, so this will be copper 2, and remember you have your ending change here, so this will be copper 2 chloride. Okay. In my next example, you want to do that cross-up step. So we're going to bring the 2 up to the oxygen. Because there is nothing on the oxygen, we're bringing up a 1 to the copper. You always, always, always check your negative. So if we take a look, oxygen is indeed a -2, so that is correct. That means this is correct. If your negative is matching up with what it should be, then you are ready to name it. So we still have copper, like the example above, but we have a different charge for that copper. It is a 1. So we're going to include a Roman numeral 1. And then we have oxygen. So we changed its ending. So we have copper 1 oxide. In this next example, we have subscripts on both of our elements here. So we're going to bring up a 3 to the iron, a 2 to the sulfur. You verify your negative. Sulfur is indeed a -2 charge, so that is correct. So that means the positive is correct. So Fe is the element iron. The charge of the cation is 3. Your ending, because it's sulfur, becomes sulfide. Okay, so the next one is where things start to change. And this is the importance on why you must do this step every time. Because right now it looks like we have a 1 and a 1 because there's no subscript. So a lot of times students will say mercury 1 oxide and move on. Mercury 1 oxide is not correct. Again, based on the subscripts I see, this would be a +1. This is a -1. You verify your negative. Oxygen is not a -1. Oxygen is a -2. So I'm going to cross this out and change to a -2. So that means Hg cannot be a +1. So if you think it through, what made that -2 disappear? What simplified that -2? That had to be a +2. So the true charge, the actual charge of the mercury, is +2, not a +1. So we would name this mercury 2 oxide. So again, your subscripts, the lack of, or even the subscripts that are there, can lie to you, and you have to verify it. So again, that's why this cross-up method is so important that you don't skip. On this last one here, we have FEN. So we do the same thing, just like the one up above. We get a +1, -1 because there is no subscripts present. You then check your negative. Nitrogen is not a -1. Nitrogen is truly a -3. So what made that -3 disappear? A +3. So when we go to name this, this is iron 3 nitride. Again, you always use the true charge, and that's why you have to kind of work it out in these steps. And so that's the part that starts to become difficult for students, is figuring out what goes in that parenthesis set. So the right-hand column of this table, this next set of 2 puts a different spin on things yet. We're at the same thing. Cross up your subscript. So we bring up a +2 to the tin. We bring up a -1 to the sulfur. Just like before, we check our sulfur out. It's lying to us. Sulfur is not a -1. It is really a -2. Well, if I keep it like I have it, +2, -2, my formula would just be SNS. That is not what I have. So that means that something had to simplify. So tin cannot be a +2. What could I have crossed down with the sulfur that would simplify out that -2? Well, if you go up to your next even number, let's try a +4. So if you try this out, we have +4 -2. We get SN2S4, which indeed simplifies. So this is a lot like algebra in that you can check your work. This is the correct formula that I have. So that is the correct charge. So when I go to name it, this would be tin 4 sulfide. So again, you can always rework it out, kind of like substituting in an X to make sure that charge works. The next example, cross back up. So I'm going to bring that 2 up to the carbon, nothing on the carbon, so that's bringing up a 1 to the mercury. Checking out carbon, we have a -4 charge. So that means this is a lie and that this is a -4. If I were to work it out using that technique, this would say that Hg4C. That does not match up. So that is not correct. Mercury is not a +1. So again, like the tin, something had to simplify with the 4. Go up to your next even number, which is a 2. Work it out. So we have Hg +2, carbon -4. We get Hg4C2, which is simplifying to Hg2C. That does match up. So that means the correct answer for this one is mercury 2. Carbide. So the last three examples are like what we just saw. The only difference, the only change is we now have a polyatomic. So you'll have to use your polyatomic list to verify your negative charges versus the periodic table. The other thing you have to be careful of is what are you crossing up to your cation. So you have to keep track of what do your subscripts mean. So this PO4, if you look, is phosphate. So that 4 is there as part of the polyatomic formula. It's not there because of charge. How I know that is that phosphate is not in parentheses. So what that really means is because the phosphate is not in parentheses, is that Ag is a +1. I'm bringing up the -3 to the PO4, which if you verify, PO4 is a -3. So this is correct. This is correct. So Ag is silver. The charge of it is a 1. The polyatomic is phosphate. So as we look at the next example, we do see Roman numerals, or excuse me, not Roman numerals, but parentheses. So what you see outside of the parentheses versus here, so I didn't have parentheses, I brought up a 1. Whatever you see outside of a set of parentheses is what you are going to cross back up. So I'm bringing up a 2 to the cobalt. I'm bringing up a 1 to the NO2 because there's no subscript there. That should hopefully be the end of the Bell trio that we have going on here. So we have NO2. When we go looking for it on our polyatomic list, it's here. That's nitrite. And if I verify, the charge is indeed a -1. So I'm ready to name this because the anion charge is correct. That means the cation charge is correct. So we would name this cobalt 2 nitrite because I have 2 oxygens, not 3. Last example then for the notes. So same idea. I have parentheses like the one above. So I'm bringing that 2 up to the PB. I'm going to bring up that 1 to the SO4 because there's no subscript here. Do my verification steps. So SO4, we're going to use this one a lot, is sulfate. SO4 is really a -2, so this is lying to us. So not a -1, but a -2. If I try it with that +2 -2 combination, those would cancel and our formula would look like this. That is not what we have, so this is not correct. Hopefully you can see that something had to make that 2 appear, so this was a simplification. So that means lead here has to be a +4 charge. So this is really going to be lead 4 sulfate. So I know in chemical naming, this one gets to be particularly challenging, especially going from the formula to a name. You need to go through and do these steps where you cross back up, you verify your anion. If it doesn't work out, you need to determine what is the true charge of that cation to give you the chemical formula provided. If you want me to check something over, if you are needing a little bit of extra help, please let me know and we can definitely set up a Google Meet and I can help you out. So just take your time with the homework and again, let me know if you have questions.